Okay, great. All right, so let's we 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 had done polarization, and there are some questions that we had to do in polarization because for the rest of static electricity and even for current electricity, you have to have some basic understanding of polarization. All right, so let's do the questions very quickly and then move on to the next topic. So question one, a rubber balloon possesses a positive charge. If brought near and touched to the door of a wooden cabinet, it sticks to the door. This does not occur with an uncharged balloon. These two observations can lead one to conclude that the wall is. So you have a rubber balloon. So let's go back. So a rubber balloon with a positive charge. It is brought near and touched to the door of a wooden cabinet. It sticks to the door of the wooden cabinet. Okay? And this would not occur if the balloon was uncharged. So the balloon being charged, it sticks to, we know that the wooden cabinet, it's an insulator. It's not a conductor. It's a neutral object. Okay? So we're seeing a charged object. Um, these two observations can lead one to conclude that the wall is electrically neutral. So let's just think about it. If okay, the balloon is positive. If the wall was if the wall is negatively charged, yes, you would get an attraction there. Okay. Um, but we know that the wooden cabinet is a neutral object, and we know that neutral objects is attracted to charged objects, whether it's positive or negative. Neutral object is attracted to charged objects. So the the wall is electrically neutral, and we explain why charged objects is attracted to neutral objects. That is because a neutral object, or so okay, so you have a positively charged object. When it comes in contact with a neutral object, it's going to pull this positive charge is going to pull the electrons towards it in the neutral object. So that is why it sticks. And if it was a negatively charged object that comes in contact with a neutral object, it's going to push away the electrons. So the positive charge are going to be there, so it's going to stick. So that is why a charged object always attracts a neutral object. All right, so question two. Which of the diagrams below best represents the charge distribution on a metal sphere when a positively charged plastic tube is placed nearby? All right, so in case A, you have a positive charge tube come in close proximity to a metal sphere. So this doesn't make any sense because you have a positive tube. What you expect to happen, since this is a metal sphere, it's a conductor, it's going to pull the electrons close to it. So the electrons are going to line up over this side. So this scenario doesn't make any sense. Again, you have a positive tube here. It's going to pull electrons. Remember, the protons are in the nucleus, and they usually don't move. They usually don't move. So if you have a positive charge tube, it's going to pull electrons. Okay, this one doesn't make any sense. So this makes sense because you have a positive charge tubes. It's going to pull electrons from this side of the sphere. The electrons are going to crowd over here, And because the electrons move from over here, then this side is going to be positive because the electrons move away. So they essentially lose their electrons. So now they become positive. Okay, so for number 2, it's D. And then 3, all right. So we did talk a little bit about polar bonds. And question 3 relates to polar bonds. So the distribution of electric charge in a water molecule is non-uniform. Uh, the more electronegative oxygen atom attracts electrons from the hydrogen atoms, and we showed that. Oxygen tends to attract the electrons from the hydrogen atom. So the oxygens tend to be negative and the hydrogen atoms tend to be positive. Thus, the oxygen atom acquires a partial negative charge and the hydrogen atom acquires a partial positive charge. The water molecule is polarized. It's not charged, it's polarized. Which diagram below correctly portrays a pair of water molecule and explain. Let's look at case A. So this is our water molecule up here, oxygen and 2 hydrogen. The oxygen going to be slightly more negative, the hydrogen going to be slightly more positive. So it's, if the hydrogen is positive and next hydrogen is positive, they're not going to attract each other. They're going to repel. So this scenario doesn't make sense. Let's look at this one. So the oxygen is a little bit more negative. The hydrogen is a little bit more positive. So this hydrogen will attract or will be attracted to this oxygen because the hydrogen is positive and the oxygen is negative. Opposite attracts. So this makes sense. Let's look at this one. Oxygen is negative. They're going to repel. This doesn't make sense. Oxygen is negative. Hydrogen is positive. There's an attraction. So this one makes sense. So it's B and D. So a lot of it is just common sense, a little bit of physics, more common sense. Okay. Question 4. True or false? When an object becomes polarized, it acquires a charge and becomes a charged object. No. Polarization is just a redistribution of the charge. The object is still electrically neutral. It's just that the charge is moved to opposite side. That is what polarization means. Okay? So that one is false. Okay, and then question 5. Charged rubber rods are placed near a neutral conducting sphere, causing a redistribution of charge on the spheres. Which of the diagram below depicts the proper distribution of charge on the spheres? List all that apply. Let's look at diagram A. So you have a negative charge rubber rod. This is our metal sphere. So it's going to repel, so it's going to polarize the charge on the metal plate. So it's going to push the electrons, because remember, only electrons can move. Only electrons can move. Protons not going to move. So it's going to push the electrons away from this side over here. So you're going to have a positive charge there and a negative charge over there. So that's case A is good. Let's look at case B. Positive charge rubber rod. It's going to push the electrons away. So the electron is going to move. It's going to pull the electrons to it. The positive charge is going to pull the electrons. So this case B doesn't make sense because it's pushing the electron, which doesn't occur. Opposites is going to attract, so it's going to attract the electrons. So this doesn't make. And case C, negative rubber rod, it's going to repel the electrons. So electrons are not going to crowd on this side. It's going to repel the electrons. Positive rubber rod, it's going to attract the electron. So the electron is going to move from this side over here. It's going to polarize it. So D is good. And E doesn't make sense because if the electrons come over here, then this should be positive right there. So A and D make sense. Okay? Opposite attracts, like repel. All right, question 6. In the above situation, the conducting sphere is, let's all apply. The conducting sphere, all right, let's go back. Okay. So these are a conducting sphere. So so we have the scenario. It says in the above situation, the conducting sphere is, so the conducting sphere could be, it could be uncharged or neutral. Okay. And when the charged object came in contact with it, it becomes polarized. Polarization is just a redistribution of the charge. The overall charge, the object overall is neutral, electrically neutral. It's just that the charges move to opposite side. But if you were to add up all the charges, the negative would balance the positive. So it's still a neutral object. All right, so what we're going to do now, we're going to look at charging. And the first charging method we're going to look at is charging by friction. What we saw before was polarization, the charge moving to opposite side. But if you remove the object, that the charge object that caused the polarization, everything will revert back to normal. Okay, the electron is going to run back in their original place, and you're not going to have any excess charge on either side. So when we talk about charging by friction, what we do, we transfer electrons between objects by rubbing them together. That's basically what it is. So we rub objects together, and what we're trying to do is to transfer the electrons from one object to the next object. Some objects tend to give up their electrons easily. And then there are other objects that have a great affinity for electrons. So when you come in contact with materials, some material is gonna give up their electrons easily, and some is gonna have a great affinity for electrons. So an experiment, and you can do this at home. If you have a rubber tubing and you rub it with animal fur, and you rub it with animal fur, what will happen is the animal fur will give up electrons to the rubber tubing or the rubber tube. So the rubber tends to have a greater affinity for electrons than the animal fur. The animal fur has less great affinity for the electron, so it's going to give up its electron because the animal fur, the rubber has a great affinity for electrons. So a rubber balloon is charged negatively. So if you get a rubber balloon and you rub it with animal fur, the rubber balloon will become negatively charged. And because the animal fur gave up its electron, it's going to be positively charged. Because the rubber has a greater affinity for electrons, it's going to remove the electrons from the animal fur. So the rubber balloon is going to be negatively charged. And this is what it looks like. So, you have your rubber and you have your animal fur, you rub them together, the electrons slough off the animal fur and goes on your rubber tubing. So the rubber becomes negatively charged. And because the animal fur gave up its electron, it has a net positive charge. So these objects are now charged because it has an excess of electrons. so has a deficit of electrons, so they're charged. There's something we call triboelectric series, and this is just the ordering of objects according to their affinity for electrons. That is, if you put objects in order of their love for electrons, the ones who love the electrons the most are going to be on top, and the ones who love the electrons least are going to be on the bottom. So if it loves the electron more, it's going to tend to pull electrons towards it. So when we talk about triboelectric series, that's the ordering of objects according to their affinity for electrons. And this is what a series looks like. So if and you can order it in this fashion, where materials lowest on the list will strip electrons away from objects higher on the list. So what we're saying, we order it in such a way so these objects tend to give up their electrons, and then these objects lower down tend to pull electrons. They love electrons. They're a lover of electrons, as opposed to objects over here, which are giver of electrons. Okay? So if you rub these objects over here against these, they're going to give up their electrons, and these objects are going to attract their electrons. So this is what we call the triboelectric series. You're ordering objects according to their affinity, their love for electrons. All right, so we're going to move on now to the law of conservation of charge. And remember what we said, if when we polarize an object, even though we bring a charge, so we have a metal sphere, and we bring a charge in close proximity, the charge going to rearrange themselves, but the object is still electrically neutral. Okay, so, but not only that, if we charge an object by friction, the case we just show you, you use the animal fur and you rub it against a rubber. Electrons are going to move from the animal fur to the rubber. The rubber is going to be negatively charged. The fur is going to be positively charged. But if you were to add the charges, the negative charge on the rubber would equal to the positive charge on the animal fur. So the negative charge or the negative electrons move from the animal fur and go to the rubber. The overall charge of the system is the same. That is, when the object started at first, they were neutral. They weren't charged. But one object gave up its electron. So the object that gave up its electron is now positive, and the object that gains the electron is negative. But the negativity and the positivity are equal and opposite. So when you add them, the net charge is zero. So the law of conservation of charge says that the charge on objects prior to charging is the same as after charging, and the net charge is zero. So when we take two neutral objects and we rub them together, the charge on the object prior to charging is zero, because it's a neutral object. And then after charging, the net charge, because the positive is going to equal the negative, but when they come together, the net charge is zero. So that's a law of conservation of charge. And again, you have two neutral objects. The charge before, because they're neutral, they're not charged. So the charge before is zero. When you rub them together, electrons go on this cloth, and this plastic rod loses electron. So it is positive by, say, this is 10 protons, because it lost 10 electrons. So if you were, so the charge after the net charge is zero, still zero, because you have 10, 10 you have an excess of 10 protons and you have an excess of 10 electrons. So when you combine them electrically, the net charge is zero. And we start with zero charge because these are uncharged objects. Okay, the law of conservation of charge. So we look at charging by friction. You're just rubbing stuff together, and the object with the greatest affinity for electrons going to pull the electrons away from the object with the least great affinity for electrons. That's friction. Now you can charge an object by induction, and when you charge an object by induction, the objects don't actually touch each other. So you charge an object without actually touching the object to another charged object. So remember, friction, you rub the objects together. With induction, the objects are held apart. They do not touch. So you bring a charged object in close proximity to usually an uncharged object. And this is what we're talking about. So this is an example, and just pay close attention. So we usually do these electrostatic experiments by having a conductor, so a sphere, and you will have, a support, a tubing, probably a glass tubing or something like that, and then you have an insulator, some type of insulating material here. So basically what's going to happen, if you charge this sphere, the charge is going to remain in the sphere, because now the supporting structure is an insulator, so it's not going to conduct your charge. All right, so if this is a negative, you bring a negative rod in close proximity, you do not touch the sphere. What's going to happen, it's going to repel the electrons on this side. So you repel the electrons, and the electrons going to crowd the opposite side. So this is what we call polarization. Okay, the charges are rearranged themselves because the electrons don't like, these electrons over here, so they run to the opposite side. So this becomes positive and this is negative. This is polarization. However, if you put a ground on this side of this sphere, and I'll explain what a ground is, but if you were to remove these electrons from this side of the sphere, okay, so you have some method where you remove these electrons from this side of the sphere, and you still have your stuff in place, what's going to happen? The electrons over here are going to disappear because you remove them, and you still have your negative rod in place. So you're going to have a crowding of protons over this side. But once you remove your rod, there will be a distribution of the protons on the surface of the sphere. The protons are not going to move. What's going to move is the electrons, because since you have you remove the electrons from here, so you're going to have an excess of protons. When you remove this rod, what's going to happen? The electrons are going to orient themselves in such a way so as to make the protons uniformly distribute themselves. Okay, is the protons not going to move? Is still the electrons going to move? But the charge, instead of crowding just one side, once you remove your charge rod, it's going to, the protons are going to evenly distribute it throughout the surface. Okay, now this object is charged. Okay, but in order to charge an object, you have to remove these electrons. So we remove the electrons by a process we call grounding. Okay, we remove the excess electrons, and then we remove or charge negative rod. Then the protons are evenly distributed on the surface of the sphere. So this is charging by induction. We didn't touch any. We didn't use the charge object to touch the sphere. Okay. So when we say grounding or grounding or ground is just a supplier or receiver of electrons. It is just something that can either supply electrons or something that can receive a bunch of electrons. That's basically what grounding is. Sometimes you'll see hurting. Sometimes it's called hurting. And what it actually is doing, hurting or grounding, means making the object neutral or uncharged. So that is the process of grounding. You try to make the object neutral or uncharged. If the object is negatively charged, then taking its electrons, uh, um, so if the object is negatively charged, you can remove the electrons. If the object is positively charged, then it will gain electrons. Okay? So if you have an object, a sphere, which is negatively charged, and you apply grounding, you remove the electrons. The electrons you're gonna remove the electrons, so it's gonna become neutral. Okay? So you're gonna remove all the electrons, remove the excess electrons. If an object is positively charged and you apply a grounding process, or you touch it, that's all you have to do. Electrons are going to move from the ground to the object, rendering the object neutral. That is what earthing or grounding means, to make something neutral by either giving up electrons to the object or removing electrons from the object. All right. We say all of that or all of this to explain what an electroscope is. An electroscope is a very important device. It is capable of detecting the presence of a charged object. Okay, so if you have an object and you want to determine whether it's charged, yes or no, you can get an electroscope and you can check to see if it's a charged object. The two types we're going to mention is one is a gold leaf electroscope and the other one is a needle electroscope. And this will come in your exam in some fashion. So this is our um, needle electroscope, okay, and I'll explain how it works. Basically, everything here is a conductor. So you have this knob right there. It's a metal tubing going all the way down, and then this is a metal tubing. This is a metal tubing. What happened is this needle usually is vertical, lying right beside this vertical metal tube. Uh, so if these two metal objects, if they're charged similarly, they're gonna move apart because remember, like charges repel. So if this is charged positive and this is charged positive, they're gonna repel each other. So it's gonna move away. You're gonna see the needle flickers. If they're neutral, however, they're both gonna be vertical. We'll explain that. So this is our gold leaf electroscope. Electroscope is a device that just tests for charge. So if you have an object and you bring it in close proximity, you're not touching it. You bring it in close proximity. If it's charged, something going to happen. So again, this is all metal conducting material going all the way down, and then these two leaves are metal. Okay, so if you were to charge this system, and the each leaf is charged with the same charge, they're going to repel each other. So they're going to spread apart. The leaves are going to spread apart if they're charged similarly with the same charge. If they're neutral, they're going to touch each other. They're going to come, uh, they're going to be right beside each other. They're going to close. The leaf is going to close. This is how an electroscope works. Electroscope is a device that just going to check for charge. If something is charged, it will register it. Remember what we said, that these this is the leaves. The leaves are usually parallel and touching each other. If you bring a charged object, if say you bring a positively charged object in close proximity to this electroscope, this metal plate on top, because this is positive, it's gonna it's gonna attract the electrons, and the electrons gonna crowd on the surface. The electrons want to jump over to this positive rod, but you didn't touch it. The electrons are just gonna so they're gonna move from down here and crowd up here, and because the electrons move from here, these structures down here are going to be positive, so they're going to spread apart. Okay, so the the positive rod is going to attract the electrons. The electrons are going to crowd up here. They're going to come from down here. So each of these plates is going to be positive, and because like repel, they're going to push apart. They're going to separate themselves from each other. Okay, so once we see this phenomenon, we know that this object is charged. Okay, let's look at the leaf again. So again, you have a metal pan right there. You have a metal rod. They're all conductors now. The metal rod, and then this is metal. Okay, metal foil in the form of a leaf. If everything is neutral, they just lie parallel. If you bring a negative rod in close proximity to the metal pan, it's going to push the electrons away. So the electrons are going to go down to the bottom and leave the positive charge on top, because that's what these electron wants. Okay, it's going to push the electrons away. So up here is going to be positive, and the leaves are going to be negative. Because the leaves have light charge, they're going to repel each other. So they're going to separate, and you can see that. The leaves separate. Similarly, if you have a positive rod and you bring it in close proximity to the metal pan, it's going to attract the electrons. The electrons are going to come from the lowermost portion, and the electrons are going to crowd up here. The leaves are going to be positive, and because light charges repel, and the leaves are now positive, they're going to repel each other. The leaves are going to repel each other. So it's going to separate. So you can see the leaf, if you any charged object, the leaves are going to separate. If it's a neutral object, the leaves are going to be parallel. Then there's not going to be any separation. So this device is called an electroscope. It just checks for charged objects. All right. So what we're going to do is we're going to stop here. There's a series of questions that we will do